Okay, so welcome. We're going to talk about section 3.5 today. It's on quadratic data modeling. Okay, and this is going to be a fairly quick and straightforward lesson because most of our work when we're doing these modeling assignments is going to be done through Desmos. Okay, so our real job here is to recognize when a quadratic model is appropriate. Okay, and so we've talked a lot over the last couple of lessons about the shape of quadratic functions, right? We get that U shape that it opens either up or down. Okay, they have obvious concavity. That concavity never changes. So these are kind of the features we're looking for in our scatter plots to help us make a decision as to when a quadratic, let me spell that correctly, model is appropriate. Okay, so I've got a few scatter plots here. This first one is very clearly a scatter plot where a quadratic model would be appropriate. We see the U-shaped graph. We see the vertex of this parabola down here, and we notice that the graph is always concave up. It's always going to hold water in that case. So this is a pretty clear example of a data set that we would use a quadratic model for. The second one is less obvious, I think. Okay, because we don't see the turning point, but this one is also one that I would certainly use a quadratic model for because of the curve, right? You'll notice this is a curved, this graph clearly is concave down, right? And if we were to use a linear model, we would not be able to capture that concavity at all. Linear models don't have concavity. They're just straight lines, right? So we would certainly want to use a quadratic model for this one because the clear concavity. Okay, now one thing that we want to avoid when we're doing our modeling is kind of forgetting about the old methods, right? Because this third data set, there's no obvious concavity to it, right? That in fact, it just looks like it's kind of increasing at a constant rate. It's not perfect. These things don't line up perfectly, right? But to me, this is better modeled with a linear graph than it is with a quadratic graph. Okay, and so the important thing to note here is we're learning new methods of modeling. We don't want to forget the old ones because sometimes they're just better. Like this third example here is one that's better modeled with a linear model than it is with a quadratic model. So that's going to be our job is to think about the scatter plot, analyze it, and then choose the model that is most appropriate based on the shape of the data. Okay, so now we're going to pop over into Desmos. We're going to look at a few data sets, and we'll practice some of this regression stuff. Okay, so here we are in Desmos. Got a table of data entered in, X and Y's. Again, you'll just be given this data in the MyMathLab problems. Okay, so the first thing I want to do is I want to zoom in on the scatter plot. I've already done that here, but remember to do that, it's very easy. You just click on the little magnifying glass, the zoom fit button in the bottom left-hand corner of this. It'll zoom us right in on the data set, right? And this one is kind of like the second example I gave you before. There's no clear turning points here, right? But we can clearly see that this graph has got some concavity to it, right? It's definitely it's not a straight line. So this is a great example of a problem that is where are going to use a quadratic model for. Okay, so to do that model, we're going to do it just like we did in Module 1. We're going to click on the Add Regression tool. Okay, you'll notice it does a linear regression by default. It's not very good in this case, right? This number is pretty far from 1, right? So, and it's not very close to our data point. So that's why we need other forms of modeling. Because linear doesn't work for everything. So in order to get a quadratic regression, we're just going to click our little drop down button here. We're going to choose quadratic regression from the list, and we can see this is a much better model. In fact, it's a perfect model for our data set because our R squared is actually equal to 1. Okay, and it's performed that regression right here. We'll notice it's in that ax squared plus bx plus c form that we've been talking about for the past couple of lessons. Okay, now it is very important when you're doing these modeling problems in MyMathLab in particular that we pay attention to the rounding instructions because we're not going to keep all of these decimal places generally in any case. So in this case, let's say we want to round this answer to 2 decimal places. Okay, so we would go with 99.83 x squared when we're entering this, plus 1.77x minus 1.79, and that would be the answer that we're looking for here. Again, just going to two decimal places, rounding based on the third digit there after the decimal to help us make those decisions. Okay, so I'm going to go through one of your homework problems with you because I do think it's quite tricky. It's question 4 from this section 3.5 homework problem. And it kind of starts the same way as the other ones, but does give us some context, and there are some very tricky things in this problem. So I want to kind of go through this one specifically with you. Okay, so we get this table of data that estimates the number of Alzheimer's patients uh, in a particular country in millions. Okay, for the years 2000 to 2050. Okay, so we've got this table of data. Okay, and you'll notice the first question here asks us to create a scatter plot of the data where X is the number of years after 2000. So this is very important to note. We're not going to put 2000, 2010. We're going to put, well, we're going to subtract 2000 from all those values and we're going to scale our years. We've seen this a lot in Module 1. It's not going to change. We're going to be scaling our years very, very often throughout this course. Okay. So I'm going to start by putting this data into a table in Desmos, paying attention to the way we've scaled that data. Okay, so I went ahead and did that over here. Okay, so you'll notice I didn't put 2000, I put the year 0, and then 10, 20, 30, 40, 50. And then my Y values, I just typed them in as, remembering that these are in millions of people. Okay, so I'll go ahead and zoom fit on this. Okay, and our data looks kind of like this. And this is one where I look at it and it's kind of linear, but I do kind of see a bit of a curve to it, like it's a little bit concave up. Okay, so what I'm going to do here is I'm going to check both a linear and a quadratic model, and then I'm going to pick the one that has the better R squared value to do here. Sometimes we need to let the Desmos do that work for us because it's very easy to check both. So if I try a linear regression, I'll notice here that my R squared is not the worst. You know, we don't hit every single point, but 0.97 is not bad. Okay. But if I try a quadratic regression, I get a much better R squared value. Okay. So 0.99 is much closer to 1. So the quadratic regression is a better option here. It makes sense because the data does have a bit of concavity to it. It's a graph that appears concave up to me. Okay. So now is where things get a little bit tricky. Let's pop back over to the question again. Okay. It asks us to find a quadratic model. And it asks us to report the model to 4 significant digits. Now, significant digits is not something we're going to focus a ton on in this class. It's not something that will be on any of your exams, but it will be on several of your homework problems because it's important, especially for those of you in the healthcare fields, right? You're going to do chemistry, biology, classes like that, and you're going to be doing a ton of work with significant digits. Okay, so let's talk about what a significant digit is. A significant digit just means we're not going to count zeros at the front of very small numbers when we're dealing with significant digits, right? So in this case, you'll notice we didn't count any of these leading zeros, okay? And these are very common in chemistry because some of your numbers are very, very small, right? So we don't consider these first 3 zeros significant. So we just start counting from the first non-zero digit, and then we keep 4 digits there. Would round based on the next digit in the sequence. Similarly here, we would not count these first 2 zeros. Okay, and then we have 4 digits after that. And then in the last number here, our C value, all of our digits are significant, so we only have 4 digits there. So the thing you'll notice when we're dealing with significant digits is we're not going to have the same number of decimal places in each of our coefficients here. That's okay, right? Because we just are counting the ones that are significant. So let's pop back over into Desmos here, and we'll kind of go through how we get that. Okay, so if I'm writing my model, putting it into Desmos, I'm going to write down these zeros, but I'm not going to count them as significant, right? So we're going to keep 1, 2, 3, 4 digits here. So 2 to 8, and then the fourth one here, we're going to round based on the digit after that. So because this 5 is my last significant digit, the number after it is 5 or bigger, I'm going to go to 6 there, then x squared. Okay, plus, again, similar logic for the second one. We're going to keep the 0.0, and then we want 4 digits after that, so 917, and then the next one's a 1. We're going to keep it as a 1 because the number after it is not 5 or bigger, so we're not going to round it up. And then for our last one here, all of our digits are significant, so 4.228, or sorry, 229, because the number after that is 5 or bigger. We've got 4 significant digits. Whoops, what am I doing? 4.229 is our C value for this particular quadratic model. Okay, so that's the big trick in this problem. Or the first big trick is that we're asked to round to 4 significant digits, so we need to understand what that means. Okay. Next, it asks us to graph. I mean, that's pretty straightforward. You've got your graph on there. You might have to change your window to make it look more like this. You'll notice the window on this, if we pop it out, well, I guess it doesn't give us the window, but our window doesn't exactly match up. But clearly, this is the only one that has the shape that we're looking for. It's the only increasing one. You know, the other ones have maxes, mins on them, so they're pretty clearly not there. Then we get to probably my least favorite problem in the entire course. It asks us whether the model is a poor fit, a mediocre fit, a good fit, or an excellent fit. It's clearly not poor or mediocre. You know, this is a pretty darn good fit to the data that we have here. I don't know what the difference is between a good fit and an excellent fit. Okay, but the answer here is good, so just choose that one. It's a little bit of a silly question. Okay. And then finally, we're asked to use our model to predict these for a couple of different points. Okay, the key thing here is we need to make sure we're keeping our scale in mind. If I'm interested in what happens in 2059, I'm going to plug 59 into my equation because remember, our scale is X is the number of years after 2000. So I just pop back over into Desmos. Probably should have just made this a function from the beginning. Oops, f of x. Okay, and then I'm just going to plug 59 into this function, and that'll give us what we're looking for there. Again, pay attention to the rounding instructions. In this case, we're asked to round to 1 decimal place, so we just go with the 17.6 there. Okay, and then finally, we're asked to determine what year does the model predict we'll have 10.2 million citizens? Okay, so the key thing to note here is that the 10.2 million citizens is a Y value. Okay, so when I go to solve this, again, I'm just going to use Desmos. I'm going to come down here and I'm just going to draw a horizontal line across that 10.2 million. Okay, and I'm going to find the point where this crosses my graph. And Desmos will find that intersection point. It's very good at finding key points like intersection points here. And then I would just round this up to 35. So the answer that we're looking for here is in 2035. Okay. So that's how I would solve this. You should have a very similar problem. Of course, your numbers will be different, your models will be slightly different, but the concepts will be the same. But that one's tricky because of the significant digits. We will see this in one more lesson in Module 3, but it will not be on your exam. Okay? But that's the concepts here. Very, very straightforward. Desmos is doing most of the work for us. We just need to make sure that we're using the appropriate model. There's a very good chance that I might put a couple of modeling problems on the exam. One of them will be a quadratic for sure. It's possible, though, that I also put a linear modeling problem on the exam as well, because I don't want you to forget that we have options when we're doing our regressions. Okay, so hopefully that's helpful. Please let me know if you have any questions at all. I'll be back with another lecture video a little later today. So you all have a good day, and let me know if you have any questions.